Hi, I'm Olivia, everyone's favorite math teacher, and we're going to continue examining graphs without actually having to look at the graphs themselves. This time, we're going to look at Rolle's theorem and the mean value theorem. So the first theorem we're going to talk about is something called Rolle's theorem. And what this says is that if we have some function that is continuous on a closed interval, differentiable on that same open interval, and with the endpoints that are equal to each other, then what we know is that somewhere on that function there will be a critical value, meaning that the derivative of that point somewhere in that function will be equal to 0. And when you think about it, that should make sense, because there would be no way for you to draw a function between those points that met the criteria of being continuous and differentiable on that interval where you wouldn't have that critical value. Because either you would be a constant function, meaning every single value would be a critical value, or you would have some kind of curve where you would have a maximum or a minimum. Go ahead and try it. See if you can do it without that. Pause the video. Yeah, it's not possible, right? Because either you meet the criteria or you fail one of those two situations. You have some kind of missing value or you aren't differentiable, right? And it's actually pretty easy to prove using Fermat's theorem too, because basically you just show that, sure enough, when you go to draw this, you get something like, for example, here. And we would say that, well, if A and B are greater than every value within this curve, then sure enough, there must exist a point within the curve that is less than A and B, and that would be a minimum. And then if A and B are less than some point in the function, that point would then be the maximum. And you simply apply Fermat's theorem to Rolle's theorem. Now, Rolle's theorem is what we call an existence theorem, meaning that all it tells us is that there will be some point in here that exists. Because I could say that, well, that point exists there. But I could also have a function that maybe looks a little more complicated. Maybe it's something like this. And then I would have two C's that exist. And nothing about Rolle's theorem tells me how to find it. It simply tells me that somewhere in there, there will be at least one point C where this criteria exists. And where this is useful is that it tells me when I have a situation like this, I know that I can find some critical point. And we can use this whenever we're proving other theorems later. Like, for example, when we do this with the mean value theorem next. So here's the mean value theorem. And you can think of the mean value theorem as a more generalizable version of Rolle's theorem. And you can notice that it actually has the same kind of criteria that Rolle's theorem had. So the mean value theorem says, let f be a function that is continuous on the closed interval ab and differentiable on the open interval ab. If we meet that criteria, then there will exist some c such that the derivative of c will equal the slope between a and b. Now, what this means is that if you remember, when we take the average rate of change on a function, on some interval on a function, we take the slope between the endpoints on that interval. And what the mean value theorem tells us is that somewhere on that interval, there will exist a point where the instantaneous rate of change will equal that average rate of change somewhere. And that's not necessarily obvious. So we're going to go ahead and prove this one. So the mean value theorem was actually proven to us by Lagrange, the same person who gave us this notation that we use with the little prime mark. And it was actually a pretty ingenious proof, because what he did was he applied Rolle's theorem to something that doesn't initially look like Rolle's theorem would work. Because if you remember, the idea of Rolle's theorem was that you had 2 points that were along the same line, and then you would draw a function between them. But here, we're looking at a graph where it's not applied that way. And the real genius to this was that Lagrange looked at it and said, well, it doesn't actually require those points to be on the same kind of y value. It's just that we needed the function to have the same value at those points. So the way he did this was he used a linear approximation and a curve, because at those points, the linear approximation is equal to the curve. So he took the secant, right? Because when you look at it, the secant intersects the curve at those endpoints, which means the difference between the curve and the secant is 0 at those endpoints, meaning it actually satisfies all of the things we need for Rolle's theorem. And we're actually going to go ahead and prove that really quickly. So the first thing we do is we set up our function. Our function is h of x, and it's defined as our curve minus our secant. So we have our f of x minus that linear approximation. And it's set up the exact same way we set up the linear approximation in our previous video, right? Now, when we look at this, is it continuous? Well, absolutely it's continuous, because it's the difference of two continuous functions. And is it differentiable? Well, yes, it's differentiable, because it's, again, the derivative of two differentiable functions. It's just it's the derivative of the difference of two differentiable functions. And we take the derivative to show that, right? And in fact, we're going to use that in just a moment. So we go ahead and we set that over here. And then the third criteria is that we have to meet that more strict criteria that we don't have on the mean value theorem, which is that we have to have the h of a equaling the h of b. And this is where that cleverness came in, because the way that we demonstrate this is we just show that, well, h of a is equal to 0 and h of b is equal to 0. And we do that because, well, it's the secant, which means the two intersect, so the difference is 0, and the difference here is 0. And we do that by simply plugging a in. F of a minus f of a, that's 0. And then a minus a is 0, so this term becomes 0. 0 minus 0 is 0. And then when we plug b in, we get f of b minus f of a minus f of b minus f of a. And then over here, we would get b minus a over b minus a. That becomes 1, so we get f of b minus f of a minus f of b minus f of a. That's 0. So 0 and 0. We meet Rolle's theorem. So then we can apply what Rolle's theorem says, which is that there is some c such that the derivative of h is equal to 0 at that c. So we plug that in. The f prime of c is equal to 0, but that means that that h of c, so we plug the c into here, is equal to 0. So we replace this with 0, so 0 equals the f prime of c. And then when we solve that for 0, we get f prime of c is equal to that slope. Or in other words, there exists some derivative of the function at c where that derivative is equal to the average rate of change of that function on that interval, the mean value theorem. So this shows why these existence theorems are powerful. It didn't look initially like we could apply Rolle's theorem, because if you look at the graph, this doesn't look anything like what Rolle's theorem was being used for. But with the clever application of this kind of existence idea, we were able to stretch it to something where we were able to prove a new idea. And we're then going to use this mean value theorem to prove other ideas that we're then going to stretch this entire idea of what we're talking about with calculus into ideas where we maybe didn't think we could have used it previously. Let's take a look at one of those examples. So here are some conclusions that we can draw from the mean value theorem that are actually examples we've already looked at, coming from looking at it with derivatives. This is going, I would say, backward. So we looked at a function and taking its derivative, and we saw that if we look at a constant function and we take the derivative, the result is 0. And what this is saying is that if we look at a derivative and we see that everywhere on an interval, the derivative of that function is 0, that the function we're looking at must be a constant function. And this is simply a proof of that by saying that if we pick any two x's on an interval and we were to compare the derivatives there, that yeah, it has to be true, because if we look at the line between any two of those and we see that the slope is 0, that it's got to be a straight line, which this is just a fancy way of saying that exact same thing, because remember that the derivative at c is the slope, and we say the slope is 0, that's a flat straight line, okay? And then at this point, we're saying similarly that if we have two functions and their derivatives are equal, that those two functions must be just a linear transformation of each other, meaning that we've taken one function and we've simply shifted it vertically up or down, okay? And it's the same kind of proof, just using functions instead of individual points. Now, the one caveat I'm going to give you, or the one warning I'm going to give you about this, is that you do have to make sure that when you're looking at these functions, you do meet the criteria of both being continuous and differentiable. Because if you recall, when we looked at Fermat's theorem in the last video, the function I showed you with the bouncing ball was continuous, but it was not differentiable at all points. And oftentimes, that's going to be what trips you up when you're given problems like this. So typically, we're going to be using these, like I said, they're existence theorems. We're going to be using them to prove other theorems and other features of the graphs. But there are some examples where we might use these. So let's go ahead and look at kind of where you might see these on something like an AP test, just so that they won't come out and surprise you. So go ahead and give these two a try. Now, when we're talking about the criteria, remember that you need to make sure that the function is continuous on the closed interval and that it's differentiable on the open interval. And when we're talking about the conclusion, we're saying that we want to find the points where the derivative has the same slope as the average rate of change on the interval. So we're going to look at the answers to these in 3, 2, 1. How did you do? Now, to show that this works for the mean value theorem, we simply need to show that these are continuous on the closed interval. This one's a polynomial. This one is a rational function, or radical function. So yeah, they are. And then we need to show that they are differentiable on the open interval. Now, it's important that we're talking about the open interval, because you'll notice that here, of course, we don't have a problem. Now down here, we might have had a problem, except it's the open interval, which means that we're not actually getting to 0. 0 would be our endpoint. But because it's the open interval, we're not worrying about that, right? So yeah, we're perfectly good on this situation. And then we simply have to say, okay, what would the slope be on that interval, on that closed interval? We find that, and in the first one up here, the average rate of change on that interval was 1. On the bottom, the average rate of change on that interval was also 1. And then we take the derivative and we find where would that derivative have that same slope. So we find that derivative, and then we simply say what x value would make that derivative have that slope. And in this case, that would be 1. And in the one down here, that would be the root 3 over 9. Now, I'm not going to give any additional problems for you to work on here, because these mean value theorem problems, like sometimes there's some application for them, but for the most part, they're these kinds of problems. Usually the mean value theorem is simply used to demonstrate the existence of the mean value for other types of problems that we will be looking at in the next video. So that was Rolle's theorem and the mean value theorem. I hope this overview of those two theorems helped you out, and if you have any questions, feel free to drop into the comments or join us on Discord. I'll see you in the next video.